Good day, folks. Welcome to Bright's Mind Academy, where we bring brilliance to every lesson. Now we're going to continue now with a series of organic molecule, or rather organic chemistry series of videos, where now we have already previously discussed nomenclature. Now in this video, we're going to be looking now at physical properties. Remember, I said now organic chemistry, it is a very rich content topic that is divided into 3 parts, right? So now we are on the second part now, which is physical properties. All right. Now, on physical properties, the physical properties that we'll be dealing with now are now mentioned as melting point, boiling point, as well as vapor pressure. Okay. So now these are physical properties determined by what? By the organic molecules that we've been studying, right? Yes. Each and every molecule has its melting point, boiling point, and vapor pressure. That differs from other elements, right? Yes. Remember, each and every compound, or rather organic compound, it is unique in its way, right? Yes. So now we're gonna look at how physical properties make one organic molecule unique. All right. Yes. So now the physical properties that we're gonna be dealing with, as I've mentioned, are going to be now melting point, boiling point, and vapor pressure. So we'll be looking at melting points, boiling point, and vapor pressure of now those specific elements that we've been discussing. Okay, yes. Now, we now refer to these as the dependents. Okay, let me write it here. We refer to these as the dependent variables. Dependent. Is it written like this? Dependent. Yo. Dependent. Let me see D. Dependent. Okay, yes, like that. So we call these the dependent variables. Why? Because now they're gonna depend on certain structures or certain things that we refer to as what? As the independent. So we need certain independence that we can change between molecules so that we can now compare the results. Okay, so now we're going to say the physical properties which are now our dependents depends on, okay, so they depend on certain things. The first one, okay, actually let's talk more about the strength. Okay, actually they depend on the strength of the intermolecular forces. Now we know from grade 11 we did a little bit of this topic when we're dealing with intermolecular forces and intramolecular forces. Okay, now we say now the strength of the intermolecular forces is the one that is going to tell us whether that particular organic compound we are dealing with has a higher melting point or a lower melting point or a vapor pressure. Okay, but now let's see if now the strength decreases. Okay, we know if the strength decreases now, the boiling point will decrease. There will be a lower boiling point. The melting point will also be lower. But now, what's different is that the vapor pressure in this particular case thereof, the vapor pressure will be higher. Okay, the vapor pressure will be higher. Okay, now what do we mean that if the boiling point is low and then the vapor pressure is high? Why? Now remember when it boils, when something boils, it reaches that stage where now there is vapor. Okay, let's talk about water. If you take water, about an instance, when water boils there, there goes what? Vapor. Okay, so it is the vapor pressure now off. Now, if the sooner we reach the vapor pressure, so it means if this water boils at a lower temperature, or rather, let's say that if this compound has a lower boiling point, it will boil at a lower temperature, so something like maybe 20 degrees Celsius. Then do you agree it will reach a vapor pressure faster? Okay, so if it reaches a vapor pressure faster, we are saying now it has a higher vapor pressure compared to water that boils at 100 degrees Celsius. Can you see now? At 100 degrees Celsius, at a higher boiling point, it does what? It boils again. But now the vapor pressure will be low as compared to this one, because this one has already taken much vapor. as compared to this one. So this one, okay, let me do this. This one, when at 20 degrees it boils, right? When we reach 100 degrees Celsius of this, with this element, or rather organic compound here, do you agree with me? It will be at a stage where now it is only gas. Yes, but here at 100 degrees Celsius, it is still what? Boiling water and some little bit of gas. Okay, yes. Now, I do not want to say vapor pressure is inversely proportional to melting point or boiling point. But for the purpose of explanation, I'll say when okay, the higher the boiling point, or let me say the higher the boiling or melting point, the lower the vapor pressure. Vice versa. Vice versa. Like that. Okay, the higher the boiling point, the lower the vapor pressure, vice versa. So now let's return here and say, okay, if the strength of the intermolecular force decreases, now what happens? The boiling point and melting point are going to decrease. Okay, therefore, what will happen to the vapor pressure? The vapor pressure will increase, they will be higher. Similarly, if I increase the strength now, so we will require more energy. We'll talk about that later on. We require more energy to break now the what, or rather not to break, to overcome the intermolecular forces thereof. Therefore, you're going to have what? Higher boiling point and higher melting point. But remember, since well, this one opposes the two, this one will have a what? A lower vapor pressure, like that. Okay? Now, what does our strength depends to, or depends on? Now, our strength depends on now three independent factors. These are what we call independent factors. Okay, we have three independent factors. Independent factors. If the independent is spelled wrong, I'm sorry. We require three independent factors, namely what? The first one, it is the chain length. The second one, it is the functional group, homologous series, or you can say now type of intermolecular force. Okay. Then the third one now we refer to as branching, or you can say surface area, but I prefer saying it is branching or surface area. Okay. This is the third one. Okay, now let's talk about the chain length. We just said now, Hori, the strength of the intermolecular forces, when it increases, what will happen? The boiling point will be high as well as the melting point. But when it decreases, they will be what? They will be less lower boiling point as well as lower melting point. Now let's talk about the chain length. So we are saying the longer the chain length here, if we increase the chain length, do you agree with me? We're going to increase the number of, we are going to increase the number of carbons and hydrogens in that structure of that we have, or in our organic compounds. So if we increase the number of, let me say, if we increase now the size or the length of the molecule, now we are increasing the intermolecular forces of it. Because if it is small, it is a small compound like this. Okay, maybe let's say it has a stronger intermolecular forces. But now as we increase now the chain length, we are going to increase the what? The intermolecular forces. So now we're saying if we have the longer chain length, we're going to have the what? The stronger intermolecular forces. Okay, we're going to have the stronger intermolecular forces. Do not write it like this. Do not say IMF. You're going to get it wrong. Intermolecular forces. This is for us just to explain to you, but when you use it, it's CHAI. Intermolecular forces. Okay. Now, if I have stronger intermolecular forces, what will happen? Now, remember I said if your organic compound has a stronger intermolecular force or has a stronger a chain length, a longer chain length, there will be more energy needed to overcome. Now, it means you'll need more heat. Okay, remember you cannot compare if let's say it is like this, your compound is like this. If you require heat of say let's say 10 degrees, if I increase this one, will it still will this 10 degrees Celsius be effective to this longer chain? No, I need to increase the temperature. Therefore, it means now there will be more energy. Okay, more energy now will be needed to do what? To overcome the intermolecular forces thereof. To overcome, not to break. Very, very important. To overcome, not to break. You use to break, you are out. You lose that mark. You lose that mark. Therefore, if now more energy is needed to overcome, it results in a higher boiling point, also higher melting point. But remember this one, it is vice versa. Okay, the vapor pressure will be low thereof. Okay. Now let's go to the second one, which is branching now. Which is branching. So we are saying if our what our organic compound or our compound is more branched. What do you mean? What will happen? Let's say now I had this compound thereof. If now, can you see now it is less branch or does not have a branch at all? If I increase the branch here, if or rather, let me not say if I increase, if I take one carbon here and form a branch like this, what is happening to the length of this one? Can you see now the length become smaller? Okay, so now it affects our surface area because now here, if our chain length is longer, we are having more larger surface area, right? But here, when we take one of these carbon and make it a branch, we are decreasing our surface area thereof. We are decreasing our surface area. Okay, therefore, if we are having more branch, it means now our surface area will be smaller. Okay, can you see here we had a longer, sorry, a bigger surface area, but here, since we are adding a branch, we are doing what? We are reducing the surface area. So now, if you reduce the surface area thereof, or if you introduce more branches, we are going to cause weaker molecular forces. We are going to now reduce the strength of other intermolecular forces that we have thereof, because we like it as we want it to be long so that it has a stronger intermolecular forces. Again, therefore, less. Remember, if intermolecular forces are weak, we have less energy needed to do what? To overcome the intermolecular forces. Less energy needed to overcome, not to break. Therefore, now if we have less energy needed, therefore the boiling point will be low. Therefore, the melting point will be low. The boiling point will be low. Then the vapor pressure will be high. Okay. Yes. Now let's talk about the third one, which is now functional group or homologous series. Remember, each compound falls under a homologous series, which I now refer to as a house. Whereas now a functional group, it is what? A functional group, it is what? It is now what makes that compound specifically to be special. Whereas we saw on alcohol, we had OH. Okay, we had OH on alcohol. On carboxylic acid, we had double bond OH. On on ketone, we have double bond O, but at the first carbon or the terminal carbon, sorry, aldehyde, we had double bond O at the terminal carbon. Then the ketone, we had the double bond O at the middle of the carbons. Then alkene, we had what? Alkene, we had a double bond. Okay. Then alkyne, we had a triple bond. So that is what we refer to as what? As a functional group. It makes that a compound unique. Okay, so now we have types of intermolecular forces. Okay, this one I want you to make it yo to take it like this. The hydrocarbons, okay, the hydrocarbons, hydro. Let me write it here. Hydro. The hydrocarbons have London forces. Okay, all the hydrocarbons have London forces. If you are that particular person who struggles with memorization, okay? So you're gonna say, okay, all the hydrocarbons have London forces, which are what? Alkynes, okay? Then come here straight come here to alcohol and carboxylic acid and say, okay, the one that have OH in them, the one that has OH in them have what? Have hydrogen bonds, okay? The one that has OH or OH like that. Can you see? This is the carboxylic acid as well as a what? As well as a what's this? As well as a carboxylic acid, as well as an alcohol. So we are saying these have what? Have hydrogen bonds, both of them. Then the rest of the other homologous series we have learned, such as aldehyde, ketone, ester, and haloalkane have what? Have dipole. Now, okay. I repeat, all hydrocarbons have what? Have London forces, okay? Then now you jump straight to alcohol and carboxylic acid. You said, okay, those one has what? Have hydrogen bond. Then the rest will have what? Dipole forces. Remember in grade 11 you learned dipole, induced dipole, and all of that. Ion dipole, what, okay? But here we are going to deal with gray. But now the most important part is that we just said these ones have what? Have dipole. But I want you to take note of something. All these compounds have what? All these compounds have what? Have London forces. Okay? I'm going to come to weak, strongest, and which one are strongest is fine. I'm going to come to that. All these compounds have what? Have London forces. All of them. All of them. But now when we compare them, we're going to compare them relative to what makes them the strongest. Okay? Then, did you hear me? All the compounds or homologous series have London forces. Then from aldehyde going down, they excluding the haloalkanes, they have what? Dipole. All of them excluding the hydrocarbons have what? Have dipole. Okay? Then lastly, then these ones are unique. They are the only ones that have what? Hydrogen bonds. But now that's not what I want you to learn. Okay? That's not what I want you to learn. I want you to learn that, okay, hydrocarbons have London forces. Okay? Then I want you to learn that what are these? Alcohol as well as carboxylic acid have what? Hydrogen bond. Then the rest here have what? The rest here have what? Have dipole forces. At least now you won't deal with dipole induced dipole, ion induced dipole and all of that. Okay? Yes. So all you're gonna deal with now it is only dipole forces as well as hydrogen bonds and London forces. Okay? Yes. Now I want you to look at this. Okay. I repeat for the last time, then we move on. Okay? I'll repeat for the last time, then we move on. I said, say now hydrocarbons, alkane, alkene, alkyne have all have what? London forces. Okay? Then hydrogen bonds, we find them in alcohol as well as carboxylic acid. Then these ones, aldehyde, ketone, as well as haloalkanes and esters have what? Dipole. Now, the weakest of all, the London force are the weakest, okay? From grade 11, we know that London forces are weakest Van der Waals forces, right? So London forces are weakest. Then the dipole forces are stronger, okay? So they are stronger than what? Than London forces, but not stronger than what? Than hydrogen bonds, making the hydrogen bonds the strongest of all the three. Okay? So now, if I compare between this one and this one, I know dipole is stronger. Okay? Then if I compare between London force as well as hydrogen bonds, I know it is strong. If I compare between these, I know it is strong. But now, the question is, what if now I compare between London forces? If I compare between London forces, it means now I should come here. It's either I'm going to talk about the chain length or the branching. Okay? If now I talk about the London forces only, okay, if you compare between the London forces, compare the same intermolecular force, homologous series, and now you're going to compare the same functional group. Okay? When you are talking about the chain length, you cannot say the independent variable thereof it is chain length, whereas now we are comparing an alkane and an alkene. No, this is not a fair comparison. Okay? This is not a fair comparison. If you're talking about the chain length as our independent factor, we need to compare what? The same intermolecular forces, it should be of the same homologous series or the same functional group thereof. Okay, remember we are trying to make a fair comparison thereof there. Or now, similarly here, if I have this, similarly now when we talk about now branching, the branching, they should be of what? The branching now, the important part about branching, it should have the same molecular formula. Compare same what? The molecular formula should be the same. Okay? The molecular formula should be the same. Another part again, it should be of the same functional group. Same functional group, same homologous series. And now, most importantly, they like to compare isomers. Okay? On branching, they like to compare isomers. Why? Because now we're going to say, okay, what if I have now this, okay, and I have here a branch like that, okay, and the other one, other molecule has something like what? Still the same carbons, but now instead it has a carbon on the on position number 3. Can you see these are isomers? Just that this one, the branch, it is on position number 2. This one, the branch is on position number 3. So these are what we refer to as positional isomers, because why the position of a branch, it is different, but they are of the same homologous series. Okay, and if we check here, if I were to count now the molecular, if I were to check the molecular formula for this one, it's going to be 2C5H12. Similarly for this one, it should be C5H12. So now these are very important things that you have to look into. Okay, these are the things that you have to look into. Okay, yes. Now another thing, you cannot compare branching, but you're comparing alkane and alkene. Okay, yes. Similarly, let me see another thing happen that I should mention. Remember, we are trying to have a fair comparison. If you want to have a fair comparison, it means now you should eliminate other independent factors. Remember, we have chain length as an independent factor, branching as an independent factor, as well as functional group or homologous series as independent factor. So it means now if I'm comparing the chain length, okay, if I'm comparing the chain length as my independent factor, it means now I should keep the same homologous series and functional group. Okay, the branching, if there are branch, they should be the same. Okay, if they are branched. But now what we might differ is that the chain length. Maybe if I'm comparing butane to hexane. Butane to hexane. Therefore, it is a what? A fair comparison, because why? They are of the same homologous series. What? Alkane. They have the functional group, the same functional group. What is what? Carbon single bond. Same. They have the same intermolecular forces, which are what? Which are London forces. Okay. Then also the branching, they have no branch. They are just straight chains. How interesting is that? Now, if I come to this one, what's this? What's this? Okay, let's come to functional group. When I compare functional group, I know they should be of different functional group again. The other one should be maybe alkane, if I'm comparing alkane, and maybe haloalkane. If I'm comparing alkane and haloalkane, they're off. If I'm comparing these two, I should keep the chain length the same. If I keep the chain length the same, it means now I can say I keep the molecular mass, the size, the molecular mass should be the same, okay? Or they should be of the comparable, okay? Molecular mass should be the same or comparable. So for instance, if I'm comparing 86 grams per mole and 88 grams per mole, they are not exactly equal, but they are comparable, okay? As compared to when I'm comparing 88 and 70, can you see they are not comparable? Yes. When another thing happened, the branching, I should keep it constant. Meaning, what do I mean? If I'm comparing alkane, and I can say this is an alkane, okay? All the hydrogens. Then I'm comparing it now with what? With an haloalkane. But now I should keep now the number of carbons the same. What will differ is that this is a Br. Or let me just say, this is a halogen. Okay? Yes. This is what we refer to now when we say they should be of comparable mass, molecular mass or size. They should have the same chain length. If I'm comparing this one, remember this one should be kept constant. This one, chain length constant. Can you see there are no branching? So the branching is constant. Even if I had a branch here like that, so it means here I also should add a branch here. Because if I do not add a branch here, can you see they are not of the same homologous series and they have different branches. So it is an unfair comparison. So it means I should do what? I should remove this or add it there. Okay. Similarly to branching, the branching should occur within the same molecular same homologous series, same functional group, molecular size should be the same. What will differ will be just branching. Okay. Yes. Now remember I said London forces are the weakest. Dipole forces are stronger, then hydrogen bonds are the strongest. Now, all of these compounds, okay, let me make an example. All of these compounds have London forces. Why am I saying all of them? Check. Let's look at maybe a ketone. Okay, a ketone. These are hydrogen bonds. I don't like doing hydrogen bonds. I'm tired. Okay, let me do them for the purpose of explanation. I want you to see something. If you check here, the reason I'm saying we have London forces, this compound alone, this one compound here, and this one, do you agree with me that is an alkane? Do you agree with me? This is an alkane. Let me write that neatly. Alkane. Also, this is an alkane. And I know alkane have what? Have London forces. But now there is this one that is special thereof. This one that is special. Remember, this is the functional group of what? The functional group of ketone. And remember when we defined a functional group, we said it is an atom, a group of atom, or you said it is a bond, an atom, a group of atom. That determines the physical and chemical properties of organic molecules. Now, this one is the one that tells us, okay, I have the London forces aside, but now I come up with the strongest, which are now what? Dipole forces. So now, if I'm comparing, can you see now? It means this one, we are saying now ketones are their intermolecular forces are dipole because why? They are the strongest. They overcome. They are stronger than the London forces, so they hide the London forces, but they are there. So hence, most of the time we'll just say ketones have only. Not only, we'll just say ketone have dipole forces. Okay, you can say in addition of London forces. Okay, yes. How is this going to help us? This is going to help us. We're in a position where we say, okay, I'm having a ketone again. Okay, ketone again. Let me not change the position. 1, 2, 3, 4. 1, 2, 3, 4, 5. This. Okay, let me do this. I'm having a ketone like that. Between this ketone and this ketone thereof, which one is the strongest? Now check here. I want you to check here. When you check here, I have the London forces. How many London forces do I have? Can you see here? I had 3. I cannot say I had 3 London forces, but okay, I had 3 carbons that make the London force, okay? But in this case here, I have 4 London forces, 4 carbons that make London forces. And remember, the dipole is constant. The dipole is constant for both of them, okay? The dipole you cannot compare dipole and just them, okay? This one, they are the same, dipole. It is the same. But now what will differ is that this one has what? Has a longer chain, okay? Has a longer chain, okay? Compared to this one. Therefore, I know if I have a longer chain compared to that one, it means now here I have what? Stronger London forces. Stronger London forces. I have stronger London forces on this compound number 2 as compared to compound number 1, because now compound number 1 I only have fewer London forces. Okay, so now they might ask you which one, which van der Waals forces or intermolecular forces uh, make this what? Okay, I'll find the question, because now if I put it in a way, what if I put it in a wrong way? Okay. Talk about that. Now, also hydrogen bonds, they also have what? They also have London forces, but now they also have they have London forces, they also have dipole forces, but they also have what? The most dominant one are the hydrogen bond. Let's look at this. Now, one will be in a position of saying, okay, I hear hydrogen bonds are between alcohol and carboxylic acid. So, which one between the two has the strongest what hydrogen bonds thereof? Now we are going to say what it is carboxylic acid. Why? We're going to say carboxylic acid has what? 2 sides. 2 sides. Okay, let me look at the structure. We are now trying to compare between alcohol and carboxylic acid. Which one has a what? Which one has a stronger hydrogen bond? So can you see here? We have the hydrogen bond here. The hydrogen bond, remember hydrogen bond occurs when you talk about hydrogen bond. Okay, let me move this way, like this. Hydrogen bonds occurs when now hydrogen reacts with any of these: oxygen, fluorine, and nitrogen. If I remember very well. HF, yes. NH3, NH3, ammonia. I think so. I think between between O, F, and N. But okay, in this case, we're gonna be focusing only on when H bonds with what? With oxygen. So now here, when we draw our alcohols, 2 alcohols thereof, can we see that? Okay, I have my London force here. Okay, then I have my OH there. Okay, that makes my alcohol. Then I have London forces here. Then I have my OH here. But now, the OH here, remember the O is negative and the H is positive. So now what will happen? My O here will want to bond with what? With my oxygen. Okay, like that. And we call them intermolecular forces, these ones. We call them intermolecular forces. The intramolecular forces are these ones. These ones. Between two carbons that make, like when we draw Lewis dot structure, like this. Okay, but now when we talk about intermolecular forces, are the one that determine the physical properties when the two molecules when two molecules now combine. Okay, yes. Now this is what we refer to as what intermolecular forces. Now I said oxygen is negative and hydrogen is positive, so they will want to bond there. But why are we not saying hydrogen bonding to oxygen? Can you see they already had bonded here? So this one, they are far away. They are far away. So and there is no way that they can make a bond. So we're gonna say, okay, this one has one side of hydrogen bonding. Okay, there is only one side that we can do hydrogen bonding. But now, how about um, carboxylic acid. Carboxylic acid, remember, has a what? Q, something like Q. But in that Q, I can say, I can break oxygen into O2 minus and OH minus, like that. Okay, it still gives me what? The Q. So okay, OH minus, okay? Now, here, I'm having now my Q like that, double bond O, so I need a highlighter, double bond O, OH, like that, okay? Similarly, here I have what? Double bond O, OH. But now, this oxygen will want to bond to that hydrogen. Remember, oxygen, it is negative, okay? This oxygen will want to bond with that negative. But we still have some, okay, remember here we only took oxygen, we are left with what? With OH. Here we took OH, we are left with oxygen. So now, on this part, the O will want to bond with that H. Since well the O, it is O2 minus, will want to bond with that H plus. But here, I still have the H plus that will want to bond with the O2 minus. So they will want to do what? To bond the off, like that. So this makes it, I can bond it here on the first one, but I can repeat the process and bond it on the other one. This one, you don't need to know this one. I'm just explaining to you why we are saying this one has a two side. So it means the more we have the sides of hydrogen bond, we are increasing the hydrogen bond. Therefore, we are increasing the strength of hydrogen bond. Hence, we are saying now, can you see this one has two sides, all right? So we are saying this one has two sides of hydrogen bonding. Therefore, it makes now carboxylic acid stronger, to have the stronger hydrogen bond. Okay, this one, let me say strongest hydrogen bonding. Then this one is just stronger. Let me just say strong hydrogen bonding, like that. So now you know when you compare between alcohol and aldehyde, in case we have a scenario like that, you're gonna say, okay, both alcohol and carboxylic. Do not say carboxylic acid. You're gonna get it wrong. Write it in full. Carboxylic acid have, both of them have hydrogen bonds, hydrogen bonding. Okay, but now carboxylic acid has two sides of hydrogen bonding, two sides of hydrogen bonding, and alcohol has one side of hydrogen bonding. Therefore, carboxylic acid has a stronger intermolecular force. Again, therefore, more energy is needed to overcome those intermolecular forces. These are the lines that will be playing along. Okay, yes. Now let us be in a position of us saying, okay, how about now we say, okay, we are now in a position of understanding now the London forces and all of that. How about now we teach ourselves how to interpret now the graphs? Because now I don't want us to be in a position of saying, okay, Bright Mind Academy, they have taught us how to determine to see physical properties and all of that, three independent factors. But now in an exam, there appears a graph. Then now you're in a position of not knowing how to tackle that graph. Okay, yes. Before I go there, we need to define now boiling point, vapor pressure, as well as melting point. Okay, let me use my general knowledge and say now, let's be in a position of now defining these concepts thereof. Boiling point, this one they like it a lot. Boiling point, this one they like it a lot. Okay, you won't write any paper from from March until final without boiling point appearing. It may appear twice, 3 times, or even in all your question papers that you're gonna write of chemistry. Now we are saying the boiling point, it is now that you know this definition. Do not say boiling, you are in grade 12. You do not say it is the state where now water changes to gas. You have a zero that is waiting for you. What is boiling point? We are saying it is the temperature. Okay, very important. The temperature. Okay, let me rewrite that. Temperature now at which the vapor pressure of a liquid or rather substance. The temperature at which the vapor pressure of a liquid equals the atmospheric pressure. Atmospheric pressure, the pressure that we have externally. Okay. Now, before I define others, I want us to be in a position of saying, okay, we have defined now the boiling point. How about we interpret now a graph that involves now a boiling point of certain now compounds? Okay. Now I want us to be in a position of knowing exactly how to interpret these graphs thereof. Okay. Okay. This thing is not stable. I want us to be in a position of saying, okay, I now know how to interpret the graphs. Okay. Let's say now we have now a okay, I need to define vapor pressure. I need to define vapor pressure. Okay. Okay. Oh, okay. Let's say now here we have the atmospheric pressure when we label atmospheric. Should I say atmospheric pressure? Or should I say vapor pressure? Oh, the vapor pressure. Let me just say it is the vapor pressure. Vapor pressure. Okay. Let's measure it in millimeter uh, of mercury per mercury. Now let's say now let's make our statement that the atmospheric pressure, it is equal to something like 760 milligram per mercury. Now let me take this graph and put it a little bit lower, because now I want us to be in a position of knowing how to define now a boiling point. Okay, I want us to be in a position of knowing how to define now not boiling point, rather vapor pressure. Okay, yes, good, like that. Here I'm gonna say it is the temperature there. It is the temperature. Remember, I should label in what? Okay, in degrees Celsius or in Kelvin per se. Okay. Now, let us be in a position of knowing how to define now what is vapor pressure. Okay, I need you. Cool. Okay. Let me use my general knowledge. Okay, let's also define melting point. I think I've forgotten this one. I'm gonna say melting point, it is now the temperature at which the liquid phase, oh, I still remember it, liquid and solid phase of a substance, of a liquid, or of a substance are at equilibrium in a closed system. Very, very, very important. In a closed system. I'm going to say it is the temperature at which the liquid and solid phase of a substance are at equilibrium in a closed system. Why? Why am I saying that? Because now melting point, remember now when you melt something, it moves from ice now, or a solid phase to a liquid phase. But now it is melting at an equal rate, yeah, whatever. But just know it's the temperature at which the liquid and solid phase of a substance are at equilibrium in a closed system. Okay, yes. Now, what is a vapor pressure? If I remember very well, this one, I don't know. Okay, vapor pressure, it is the pressure, vapor pressure. Okay. Okay, let me go find the definition. Okay. I've just found my definition there of before I move on, I just need to fix an error. Remember, I want to teach you everything in which now you're gonna be in a position of applying it, right? So on melting point, it is the temperature at which the liquid and the solid phase of a substance are at equilibrium only. Only, okay? What's this? The the closed system that I'm talking about is supposed to be here on the vapor pressure off. So we are saying the vapor pressure, it is the pressure, okay, the pressure exerted by vapor, okay. Can you see vapor pressure? It is the pressure exerted by vapor, at equilibrium with its liquid in a closed system. Know your definitions of by heart. Remember definition that you need to know, I'll asterisk it. You need to know that. You really need the boiling point. It is one of the ones that you should be in a position of knowing. Okay, the definitions here are true or nothing. You miss any of the keywords here, you are out. Now let's be in a position of interpreting the graph. Okay, the graph can either be in atmospheric pressure, it is equal to this one, or 1.1, 1.1,3 kPa, depending on what we are using. Okay. Let's say now, let's put 760 it here. Let's put it here and say this is 760. Okay. Now, I want you to learn how to now interpret graphs. Okay, let's say this is 100 degrees Celsius. Let me start here. 20 maybe. Okay. 40 maybe. 60. Okay. The scaling is not giving. Let me do this. Let me start at least at 10 maybe. 20, 30, 40, 50, 60, 70, 80, 90 like that, and 100 like that. Okay, let me try to move this one a little bit down now. There's no weight like that. A little bit down. Okay, these are our temperatures thereof. Then in here, I don't know which scale to use, but I'll say maybe it is something like, I'll start it here, maybe let's say 700, 700, 640, it's fine, 580, 520, 460, and 400, maybe. It's fine, okay? Then say 760 maybe here, then here 820, like that. Now I want us to be in a position of knowing how to interpret these three graphs, okay? Let's have the first one starting from here. Let's have the first one starting from, let me choose a different color, starting from maybe here, okay? Maybe here, going like that. Have the second one starting maybe from, okay, let me have this one, like that. Maybe this one starting from here, going there. Okay, I cannot keep track of what I'm doing. Continuing there. Then let's have another one starting from also, okay, let me repeat that. Okay. Now let's be in a position of knowing how to interpret these graphs. Now let's name this graph P, Q, R, R, S. Okay, P, Q, R, S. Let me hide this and zoom up a little bit down like that. Okay, let's be in a position of now. Okay, what if I told you that what we are dealing with here, we are dealing with alkanes, okay? Straight chain, straight. Okay, let me just say these are alkanes. Alkanes. Alkane. Okay, alkanes. Like that. Okay? These are all alkanes. But now, can you see there are different types of alkanes? P, Q, R, S. What do I mean different type of alkanes? Now, they have different chain length. Why? Because now, they have different what? Different boiling point. But how can we know what exactly is their boiling point? We cannot say their boiling point it is 100 degrees. When it reaches 100 degrees, it is boiling point. No. Remember what does a boiling point say to us? What is the definition of a boiling point? A definition of a boiling point, it says it is a temperature, okay? The temperature at which the vapor pressure, okay, I repeat, the temperature at which the vapor pressure of a liquid or substance equals the atmospheric pressure. What is the atmospheric pressure? The atmospheric pressure is 760 millimeter of mercury. So it means now, when it reaches this point here, that is where now we can say, okay, if it reaches that point, then with that temperature, it boils at that temperature. What do we mean? It means now, okay, can you see now, this is the atmospheric pressure, okay? This is the atmospheric pressure. Okay, cool. So what? So it means each corresponding temperature here will be the boiling point of it. It means now where this temperature and this atmospheric pressure intersect, it means now it will be its corresponding boiling point. What do I mean? Let's say now, what is the boiling point of R? Okay, what is the boiling point of R? Okay, if I check the boiling point of R, I'm gonna say, okay, let me see where it cuts. Okay, the atmospheric touches it here, right here. Then let me go down with this reading. I want to see, can you see now? It means this one at this point, this is the point where now it is, we refer to as the boiling point. Sorry, boiling point of R. Why? Because it is the temperature, it is the, as per definition, boiling point, it is the temperature at which the vapor pressure equals the atmospheric pressure. Which one is that one? This one. So where they intersect, it is the boiling point. So it means now, if I were to say P, Q, R, S, their respective boiling point, I just did for R. R, it is boiling at 90 degrees Celsius. It is the boiling point. Okay, let's look at the boiling point of P. Do you agree with me? This is going to be easier now, because now I'm going to say, okay, let me go. Remember, this is not drawn to scale. It's just an estimation. I'm just teaching you something. We'll be in a position of saying, all right, so it means now this one at 30 degrees Celsius, it is boiling. Okay, so now this tells you now, okay, if these are straight chains, okay, alkanes, it means now this one has a shorter chain length compared to this one, and this one compared to that one, compared to that one. It means now, which one has a stronger intermolecular forces? The one with the highest boiling point, which in this case, it is maybe this one. Maybe this one at 100 degrees Celsius there. Like that. It is not drawn to scale, so I'm trying to at least do. I don't know why. This pen is keeps on. Okay, I'll say, okay, this one boils at 100 degrees Celsius. So it means this one, this S is the one that has the strongest intermolecular forces, strongest London forces, okay? So this one has the strongest London forces. Why? Why am I saying it has the strongest London forces? Because now, let me not use LF. London forces. Why? Because it has the highest boiling point. This one has the weakest what? London or C. Like that. Therefore, this one has the okay, strongest. Okay, this one is strongest. So it means here, the independent factor maybe that we might look at now, because yeah, it might maybe be a chain length. Okay, so this is what I wanted you to understand now when we deal with what this type of graphs. Okay, yes. And now the relationship is that now the higher the temperature, can you see? Do not say temperature and vapor pressure inversely proportional are directly proportional. That is wrong. There is no direct proportionality here, because if it is directly proportional, it is increased with the same rate. It means at 10, if it is 460, at 20, it will be 520 with the same rate. But here the rate is not the same. So we're going to say, as the temperature of the substances increase, the vapor pressure also increase. Okay. Like that. Okay. Now, let's be in a position of looking at other type of graphs that maybe we might encounter. Then we are done for the physical properties. We move on to now. What's this? Organic reactions. Okay. Now let's be in a position of saying, okay, let's look at another graph here. Okay. Cool. And now let me be in a position of saying, okay, what exactly do I want to teach with this graph that I'm going to draw? I'm going to say, okay, I want us to be in a position of saying, okay, 1 here, 2, 3, 4, 5, Maybe let me extend this a little bit to, okay, maybe 6 and 7. Okay, I label it right now, just now. I want to be in a position of saying, okay, how about I start at 0? This is 0, right? 0, 50, 100, 150, 200, 300. But mathematics is gone. 250, 300, 350, like that. Then yeah, up to whatever. Up to whatever. Okay. Now labeling will make this make sense. What do I mean by that? Let's say now this is the molecular mass. Okay, I can say this is molecular mass, or I can say this is size, or I can say this is chain length, depending on whatever. Okay. Chain. What is chain, man? Chain length. Okay. Yes. And here, what is it? This is a boiling point. In degrees Celsius. Then this is a molecular what or molecular what in what? Molecular what in if it is molecular mass, I can say it is gram per mole, like that. Okay. Yes, depending on what the examiner might give you. Let's say now we have three different compounds. Okay, three different compounds now. Maybe the first one being here. Yeah. The second one being here. And the third one being there. Like that. Okay, let me try to repeat that. Okay, and let me name this curve P, curve R maybe. Q. Cool. Now, what exactly am I trying to teach with this one? Let's say now we have different compounds. We are comparing, agree there are three curves. Let's say on these three curves we have now, in no particular order, we have just alkanes, alcohol, carboxylic acid, and now maybe alcohol. Or let me use not alcohol, maybe. Yeah, alcohol. Let me use alcohol, it's fine. Okay. Now, what exactly am I trying to explain here? I'm gonna say, okay. Here, okay, let me change this. There's no way they're gonna start with 0 molecular mass or chain length. No way. Let me say this is 2, 3, 4, 5, 6, 7, now 8. Now, what exactly am I trying to teach with this graph? I'm trying to say, okay, if now they have the chain length, let me use a chain length for the purpose of explanation on this one. Let's say now they have the chain length, okay? If now I'm saying when the chain length, when all these graphs, when graph P and graph Q and graph R have the chain length or one carbon or one chain length like that, they have these respective boiling points, okay? So if I increase the number of chain length, can you see now the boiling points of them also increases, okay? But now the question is, I need to know which graph now represents an alkane, a carboxylic acid, or an alcohol, okay? Now this is very easy. You're gonna say, okay, let me check when they all have one carbon in their chain. Okay, let me check when they all have what? One carbon. If they have now one carbon, which one has the lowest boiling point? This one has the lowest boiling point. This one there has this higher maybe boiling point. This one has the highest boiling point. Oh, all right. But now what exactly am I comparing? I'm comparing alkane, alkene, and alkyne. Okay, and I know that alkanes have London forces. Carboxylic acid has two sides of what? Two sides of hydrogen bonding. Alcohol has one not side of hydrogen bonding. Oh, then what? Then it means now I know that London forces are the weakest of all. Are the weakest of all. So if London force is the weakest intermolecular forces, it means we will have what? Remember, if the intermolecular forces is weak, the boiling point will be weak. And we're like, oh, okay, which one is the weakest boiling point here? It is this one. So it means this one should be what? Alkane. This should be alkanes. All right. Now, I have now Kev Q and Kev R waiting for me. Between Kev Q and Kev R, which one is Kev R? Kev R, can you see it has the highest boiling point when now they have all, when they now all have what? One carbon. Okay. So which one between now? I'm only left with carboxylic acid as well as alcohol. So which one is strongest between now the hydrogen bonding between the carboxylic acid as well as the hydrogen bond? So as well as the alcohol. I know that between the two, this one has the strongest hydrogen bond. This one just has strong. Okay, so what does this mean? The one with the strongest will be the one with the highest boiling point. Which one is that? Is Kev R. Oh, so it means now Kev R should be what? Kev R should be carboxylic what? Acid. Why? Because now, can you see now it has the strongest intermolecular forces as compared to alkane as well as one side of therefore this of alcohol. Then this one is it is alcohol, like that. Okay, then I should be in a position of saying, okay, I hear this, but now, how about now I talk about now the conclusion or the relationship? Okay, what if now the examiner says, give a conclusion for Kev P. Give a conclusion that can be made for Kev P. Okay, not what is Kev P, what does, which homologous series does Kev P belong to? No, I'm saying draw a conclusion now about Kev P. The conclusion, remember, conclusion will be regards with the independent factor as well as the dependent factor. I'm gonna say, okay, actually, I'm gonna say the conclusion for these graphs, all of them, is that the longer, okay, the longer the chain length, let me write that handle. The longer the chain length, the higher, okay, the higher the boiling point. This is me using proper English, boiling point. But if you just don't know how to put proper English, you can say an increase in chain length cause an increase in the boiling point. That's also acceptable. But I'm not using the English that is very, very nice here. I'm going to say the longer the chain length, can you see, if my chain length becomes longer, what happens? The boiling point becomes higher for all of these. So this is the conclusion that we can now come with the off. I guess, yes. Then I can be asked to say, what does Kev PR represents? Kev R represents what? A carboxylic acid. Why? Why? Using now strength of intermolecular forces, I might say, okay, 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 Kev R, let's say we just concluded that Kev R, it is what? Carboxylic acid. Acid. For 5 marks, explain Explain for 5 marks why that's the case. You're gonna say, okay, the first argument that I have is that okay, Kev what? Which Kev? Kev P here. I'm gonna come and say the argument is Kev P has London forces. Okay? Then I'm gonna come and say Kev Q. Kev Q has what? Kev Q has one side of hydrogen bonding. Okay? Why do I have to just to specify what how many bonding, how many sites does it have? Because here I'm comparing two hydrogen bonding between carboxylic acid and alcohol. But if I had an maybe here instead of carboxylic acid, maybe I had an ketone which has dipole. It means I do not have the necessity to say, okay, alcohol has one site, because now I'm comparing it to other intermolecular forces. But if now I'm comparing the hydrogen bonding of two different compounds now, like this one, I'm going to say, okay, KFP has London forces, KFQ has one side of hydrogen bonding, and now KFR has two sides of hydrogen bonding. Okay, how does this help me? This helps me now to be in a position of saying, therefore, remember now, the one that has the strongest intermolecular forces will have the strongest intermolecular, this one, between this one, which one has the strongest intermolecular forces? We know hydrogen bond is the strongest, okay? So this one is just out, is the weakest. So we're gonna say, okay, have R, have what? Have R has the strongest, what? I won't say IMF, because I don't want you to use that in the exam. Intermolecular forces. Compared to, you can say, than both Kev R and P, okay? Kev R has the strongest intermolecular forces compared to both P, Kev P and R, respectively, maybe. Therefore, more energy is what is required to do what? To overcome, not break, to overcome the intermolecular forces, not IMF, intermolecular forces of Kev R than those, more energy is required to than those of Kev P and Q, okay, P and Q respectively. Therefore, hence, Kev R has what? Higher boiling point. Now, this is me now being in a position of telling the examiner that I know exactly what you mean. The first mark is that you telling us this has London forces, okay? Then telling us Kev Q has hydrogen bond, one side of hydrogen bond. Kev R has two sides of hydrogen bond. Or you can combine the statement and say both Kev Q and R have a hydrogen bond, but Kev Q has one side of hydrogen bond. But can you see now you're wasting your time? So already you have 3 marks here by now being in a position of outlining. Okay, outlining, or sometimes the examiner can make it 1 mark. Okay, now telling us, okay, Kev R has the strongest intermolecular forces. Even if you end here, your mark is here. Okay, Then now, if now the molecular forces is higher or is stronger, therefore there will be more energy required to overcome the what? The intermolecular forces of curve R. Okay, then this is your mark. Then if maybe the examiner continues, hence curve R has higher boiling point, maybe. Yes. Okay. This is now us being in a position of knowing how to interpret what graphs now. Okay. Sometimes they can just give you a graph like this, just a mini graph, and say this is temperature, and say let's say this is water. Let's say this is water, and say this is atmospheric pressure. Okay, vapor pressure. But here and there they say this is 1,1.3. This is measured in kPa. This is 1.1.3,3. This is what? This is a vapor. We all agree that 1,1.3 it is what? It is a atmospheric pressure. Okay. Then now they maybe create a graph like this. Maybe I need to put this one down a little bit. Maybe I need to put this value down so that I can make my graph neat. Then let's say this is 1.1.3 now kPa. Okay, we know that this is what? This is our atmospheric pressure. Okay, it is also there on the table of what. Then now they do a graph like maybe like this. Okay, maybe like that. Now we know that, okay, at this corresponding y value like this, let's say this is x. X will now represent what? X will now be in a position of representing the what? The boiling point. X will now be the what? X will, X will be the boiling point. Like that. So yeah, that's all. That's all from me on this video day off. I think I explained thoroughly now what you need to be in a position of understanding. Okay, you need to be in a position of saying, okay, now I understand now what intermolecular forces and now the dependent factors. Okay, the dependent factor is what we are trying to determine. You remember we are trying to determine either the melting point, boiling point, or vapor pressure. Now, what do you depend on? Okay, you're going to depend on what? On the independence, which are now what? Chain length, chain length, chain length now here, or now the type of intermolecular forces or homologous series, or you can say now functional group. Then, or now the third one, which is now we refer to as what? As branching thereof, and saying, okay, I'm now in a position of understanding very well what each of these now homologous series, the type of intermolecular forces each homologous series has. Okay, so I said, remember, if you want to remember this, you're going to say, okay, alkanes, alkane, alkene, alkyne, all of them have what? London forces. Then I go to the last ones, alcohol and carboxylic acid have what? Hydrogen bond. Then it means the rest have what? The dipole forces, the one that are remaining. If you can't remember well, you can say, okay, aldehyde, ketone, ester, as well as haloalkane. You are really asked of ester, okay, but just know it for fun's sake. Okay, yes, so thank you very much, folks. Please meet me again where now we'll be in a position of discussing now organic reactants. Then we are closing the chapter. You are closing the chapter of organic chemistry. It is very important to know organic chemistry, all of it, because now it contributes now 50%. I'm lying. 50 marks of your question paper. On paper two, organic chemistry alone. Organic chemistry alone. Okay. Organic chemistry alone contributes 50 marks out of 150 mark question paper. So it is 1/3 of your question. So if you know all organic chemistry and if you are good with organic chemistry, you already have now 33% of your question paper. 33%, which is 1/3. Okay. Remember, if you can master 50 out of 150, which is 1/3, which is now 33%, you haven't gone anywhere. It's just you taking question 1, question 2, and question 2, question 3, question 4 on paper 2, making sure you master it. At least the minimum, if you fail to get that 50, get 40 then. Get 40 then. Okay, get 40. Then you have to move on now to what? Reaction rate, chemical equilibrium, and now acid base, electrochemistry, now electrodynamics. Sorry, that is paper 1. Electrolytic cell, or now being in a position of talking about what? Galvanic cell. So thank you very much. Join me on the next video where we'll be discussing now organic reactions. And now many people struggle with those, but it is just a matter of understanding. So thank you very much. Let's meet on the next video. Thank you.